Now, having discussed what they called measures of central tendency, which is basically averages using mean, median, and mode, let's talk about what they call measure of variation. So to get started, let's talk about what variation stands for. A third way to describe a distribution is by its variation, which measures how much the data values are spread out. So these three pictures here, the one on the left is very narrow and tightly packed into the middle. We say that has low variation. As it spreads out, we say it has higher variation. So variation describes how widely the data values are spread out from the center of a data set. Let's look at some particular numbers to kind of get a sense of what this means. This is some imaginary numbers for, let's say, two banks and the waiting lines for these two banks. One of the banks has 3 lines and the other one has 1 line. And you can see the numbers in minutes for a particular sample of waiting times for different customers. Now, if we were to look at the mean and the median of both of these, we'd find out that it's actually the same. Even though the numbers do look different, calculating the mean and the median, we get the same value either way. But we can tell that there's more variation. The waiting times will vary more at one of them versus the other. So it says big bank, where they go all the way from 4 up to 11 minutes, versus the other one, which only goes between like 6 and 7 minutes. So there is much more of a variation there where it's spread out from smaller to larger values, even though the mean and the median are the same. And here's the histogram to show. You can see the distribution and how one of them, the values are more spread out than the other. So we'd like to know, how are we going to measure this variation? Kind of like how we measure the mean, the median, and the mode for the average. How do we measure then another number to go along with it to help us understand the spread out, how much spread there is in the data, how much variation is there? One particular way, the simplest way we could start, is by doing something called the range. The range is for a set of data values, is the difference between the highest and the lowest data values. So you're basically going to take the largest number and subtract away the smallest number, and we call that the range. Although the range is easy to compute and can be useful, it occasionally can be misleading, as we're going to see in this next example. So we have here 2 different grades for 2 quizzes, quiz 1 and quiz 2. Which has greater variation, and which one has the greater range? Well, to calculate the range, all we do is take the biggest number minus the smallest number. So for quiz 1, that would be 10 minus 1 equal to 9. For quiz 2, that would be 10 minus 2, which is equal to 8. So the range, 9 versus 8, is bigger. But looking at the actual numbers, which one is more spread out? Has more variation to it as well. While quiz 1 has the larger range in terms of the number we get, we can tell that quiz 2, on the other hand, the numbers are more spread out because there's different values that we see. So we say that quiz 2 actually has a bigger variation to it than the other one does. So while the range is easy to calculate, as we can see, it can give an inaccurate representation of variation. We most generally describe variation as a result by using calculations for variance and standard deviation. So let's talk about these now, variance and standard deviation. The deviation here is for a data value. It says deviation for data entry x from the mean mu of a data set is given by taking the number x minus the mean mu. That's the so-called deviation. How far apart are they? We subtract the 2 numbers. So to calculate what we call the population variance for a set of n values, and they use the letter capital N here, we use this formula. We call it sigma squared is equal to the summation of x minus mu all squared, that all divided by capital N. And the population standard deviation, which is just the letter sigma, not sigma squared, is equal to the square root of the formula for variation. So there's more stuff going on here than we've had to deal with before, but again, revolves around the idea of subtracting numbers, and then we square it, and then we add, and then we divide. And in the case of standard deviation, we also have to take the square root as well. So here are the two formulas side by side for variance and standard deviation. And specifically, they're calling them population variance and population standard deviation. Notice that the standard deviation is just the square root of the variance. So variance is sigma squared. Standard deviation, they use the letter sigma for it. And standard deviation is really the one we're most often going to use because the units that we get out will agree with the units that we see in the data values. Variance is not the same because it's squared, so it'd be squared units. Standard deviation would actually be in the regular data units that we started with. So let's talk about it step by step in the individual parts that go into this formula for standard deviation. The first part of the formula has us calculate each deviation from the mean. That is, we're going to take each value that we have in the data set and subtract the mean away from it, which is the formula part that says x minus mu. Step 2 is we're going to square the differences. In other words, square the numbers that we get after doing the subtraction. So we take the value minus the mean raised to the second power. Then we're going to take the sum of all the numbers that we got from step 2. So I have a list of numbers, we add them all up, and that's where that little symbol sigma comes in. The sigma symbol is there to stand for taking the sum of the values. And then step 4, we're going to divide the sum that we get by the capital letter N, which is again standing in for the number of values we have. Then the last step is we take the square root, and then we call that the standard deviation denoted by the symbol sigma. Let's take a look at some actual numbers, and let's calculate the standard deviation on this data set here. So first thing we need to do is to determine the mean of our data values. So to do the mean, mu is the letter here we use for population mean. The sum of all the values divided by the number of values. And this was the formula from the previous section that was mentioned. Sigma x divided by capital N. Again, it's just a way of saying take the sum of all the numbers divided by the number of values. And there are 5 values here total. So we'd say capital letter N is equal to 5, if you want to think of it that way also. So that's equal to, we come out with a mean of equal to 42 in this case. And then to do the standard deviation, we start by taking each number, each value, and subtract away the mean from it. So that would be x minus mu in our formula for standard deviation. So the first number is 42, subtracted by 42. And then we do 44 minus 42, 36 minus 42, 54 minus 42, and 34 minus 42. Okay, and we'll get numbers out like 0, 2, -6, 12, and -8. The next step is to square these numbers. As a result, what we're going to get here is 0, 4, 36, 144, and 64. And now what we need to do is to take the sum of all these numbers together. If we add them all up together, we get a sum of 248. So our formula for standard deviation sigma equal to the square root summation x minus mu all squared divided by capital N would be equal to the square root 248 divided by 5, which is the square root of 49.6, and that's approximately rounded off to 7.04. This number, we can think of it as measuring, again, the variation in our data set. Another way of thinking about it is it measures, on average, how much its data value deviates from the mean. So on average, how far do the numbers spread out away from the mean. On the other hand, if we're talking about a sample versus the population, we do a lot of the same things, but there's one slight difference in the formula for standard deviation and variance. We say the sample variance, rather than using the letters or the Greek letter sigma, we use just the letter s, lowercase s, and say that sample variance s squared is equal to the summation x minus x bar raised to the second power all over lowercase n minus 1. And the sample standard deviation will just be lowercase s equal to the square root of the formula for variance, where lowercase n is the number of entries in the sample. So rather than using capital letter N, we're using lowercase n. That again is to differentiate between sample and population. The biggest difference here is the use of n minus 1 in the denominator versus when the population we just use the number itself without subtracting 1 away from it. You might also notice they use x bar instead of mu, and again that's just an indicator again for mean, but for sample instead of population. Let's try the formula out on this data here, which is supposed to be a sample set of data. Okay, so here's our setup now for a sample, and we've got 5 values and our formula for standard deviation. As we did before, we need to start out by finding the mean, because that's part of our calculation here. So for the numbers we have here, we use the x bar notation in general for sample mean, and that's the summation of all our data values divided by the number of values. So we're going to add together the numbers divided by the total number of values, which is 5. This is going to be equal to 270 divided by 5, which is equal to 54. And that's our sample mean. We'll start much like we did in the last one by taking each value and subtracting the mean away from it. So things like 40 minus 54, 66 minus 54. We'll get numbers like negative 14, 12, negative 6, 1, and 7. Then we're going to need to take these numbers and raise them to the second power. So we'll get numbers like 196, 144, 36, 1, and 49. And like we did last time, we'll need to take the sum of these numbers. So when we add them up together, it comes out with a total of 426. And so according to our formula for standard deviation, we'll take the square root 426 divided by the number of values minus 1, lowercase n minus 1. So that would be the same as the square root. And we do the division here, and we get 106.5. And the square root of that rounded off to 10.32. So in summary, let's go through the notations we now have. Mu is the symbol we use for population mean. X bar is what we use for sample mean. Sigma is population standard deviation, or we use the capital letter N to stand for the number of population data values. Lowercase s is the sample standard deviation, and we use lowercase n to stand for the number of sample values. When talking about distributions, there's one in particular that we're going to spend time on, and it's a symmetric bell-shaped distribution of data, and it has certain properties and that we often see it in the real world. For instance, consider a human characteristic such as height. Most men and women have heights clustered near the mean height for their gender. But as we consider heights far off from the mean, we have fewer individuals. This tailing off of heights far from the mean produces what we call the bell-shaped curve. It looks something like this. It was symmetric, where the mean, median, and mode are all in the middle, and that's where the majority of the data values will lie. And if we know the mean and the standard deviation for a bell-shaped distribution, we usually know how it's shaped and how spread out it's going to be. We can pretty much tell a lot about it just from those two numbers. And that gives rise to what's called the 68, 95, 99.7 rule for a bell-shaped distribution, sometimes referred to as the empirical rule. So if you see empirical rule in any of the text, then it's referring to this 68, 95, 99.7 rule. What it basically means is 68%, or more precisely 68.3%, just over 2/3 in a bell-shaped distribution will fall within one standard deviation of the mean. So you can tell well over a majority fall within one standard deviation of the mean, mostly kind of clustered in the middle. But as you spread out, 95%, or more precisely 95.4% of the data values fall within two standard deviations of the mean, and 99.7% of the data values fall within three standard deviations of the mean. So the picture here is meant to show how the mean is in the middle, and as we move on either side of the mean in the middle, what percentages do we have contained inside of there. Let's look at this in more detail. So this is the picture here where you have the mean in the middle, see mu in the middle, and then like +1 sigma, -1 sigma. Those are adding and subtracting the standard deviations on either side. Let's look at a specific example and kind of talk through that as well. This is the pulse rates for adult males with a mean of 70 and a standard deviation of 11. So in the middle is the 70, and if we were to go through here and subtract 11 and add 11 to the 70 in the middle, we'll get 81 and 59. And if we measure that area within one standard deviation, we find 68% of the area lies between 59 and 81. If we go a little bit further out, subtracting 11, adding 11, adding 11 again, subtracting 11 again, we spread out to 92 and 48. So between 48 and 92 is two standard deviations of the mean. There would be 95% of the area lies between there. So we're going to use the standard deviation. We're going to add and subtract to spread out from the mean, and this rule will tell us what percent lies in between those locations inside of the bell-shaped distribution. So let's consider an example where we're given mean, standard deviation, and the fact that it's along a bell-shaped distribution. It says consider an exam taken by 1,000 students. The scores are distributed with a bell-shaped distribution, mean of 75, standard deviation of 7. We're going to use that along with the empirical rule for 68, 95, 9.7 to find the percentages that score above 82 or below 61. So if we imagine a bell-shaped curve, it tells us the mean is 75. So here in the middle, I'm going to put 75. And then the standard deviation, sigma in this case, is equal to 7. So what I'm going to do is I'm going to add 7, subtract 7 to each side, and spread out from there. If I add 7, it'll be 82, 89, and 96. If I subtract 7, we have 68, 61, and 54. So the first question to ask us is what percentage is above 82? Here's the way we can look at it. 82 is one standard deviation from the mean. And what it tells us is between one standard deviation on either side of the mean is 68%. And so if we look at it that way, then let's think about how much is left over on either side. As always, everything has to add up to 100% if we go across the whole thing. So if we take away 68 from 100, we're left with 32% left over. We split that 32% in half between each side. So on the right side we'd have 16%, and on the left side we'd have 16%. so that it all adds up to 100%. So if we just want the area that sits above 82, according to this, that would be 16%. If we want to look at the percentage that is below 61, we'll follow along the graph and see that 61 is 2 standard deviations from the mean. So if we think about what's in between here, between 2 standard deviations on either side, it said that there's 95% inside there between those two values. So in this case, that would be between 61 and 89. There's 95%. What does that leave left over on the left and the right side of our bell curve? Well, if we took 100% and we took 95 away from it, that leaves 5% left over on the outside, either left or right side put together. And if we take half of that, that leaves 2.5% on the left side and 2.5% on the right side. That adds up to 5, and with 95 adds up to 100. So the answer to what percent fall below 61, that would be 2.5%. So here's a summary of the standard deviations in our bell-shaped curve and what percentages we have inside and outside. 1 standard deviation, 2, and 3. This is available in my slides posted online if you'd like to go back to it and refer to it for any other calculations we may need to do. There's a follow-up formula that goes along with our distributions and the discussion of percentages. It's called Chebyshev's theorem. And Chebyshev's theorem says that the portion of any data set lying within k standard deviations for k greater than 1 of the mean is at least 1 minus 1 over k squared. So for just an example, if k is equal to 2, then that's 2 standard deviations. And in any data set, not just the bell-shaped one, not just the bell-shaped curve distribution, any other data sets that might have different distributions, this formula says that at least 1 minus 1 over 2 squared, which is equal to 3/4 or 75% of the data lies within 2 standard deviations of the mean. This is a lower floor, not the absolute number that would be there. So it's sort of an approximation of at least this percent will lie within 2 standard deviations of the mean. And we saw for bell curves that 95% was in 2 standard deviations for the mean. So for bell-shaped curves, bell-shaped distributions, the percentage is higher. But for other types of distributions, it may be lower, all the way down to 75%. If we went up to say k equals 3, then that's 3 standard deviations, and our formula would go 1 minus 1 over 3 squared, which is equal to 8 over 9. As a percentage, that would be 88.9%. That would mean that 88.9% of the data would lie within 3 standard deviations of the mean in any data set. So let's use the Chebyshev's theorem to do some calculations on a particular scenario here. It says there are dozens of personality tests available on the internet. One test, scored on a scale of 0 to 200, is designed to give an indication of how, quote, personable the test taker is, with higher scores indicating more so-called personability here in this case. But let's consider the scores that are there. Scores on the test have a mean of 108 and a standard deviation of 23. And according to Chebyshev's theorem, at least what percent of scores lie between 62 and 54, or another one says at least 84% of the scores lie between what two values? All right, so to get started with the first question, what percent of scores lie between 62 and 154? Let's think about our mean and standard deviation here. So the mean, let's think about it right here, is 108. And then the standard deviation, kind of like we did with the bell curve, let's go on either side of the mean, add and subtract the standard deviation of 23. So if we add it twice, it'll add up to, let's see, 131 and then 154. If we subtract it, it'll go to 85 and then 62. So what we can highlight here is the numbers that they're telling us, 62 and 154, are 2 standard deviations from the mean. And using this Chebyshev's theorem, we needed to know how many standard deviations from the mean. So that means the number for k in the formula is equal to 2. And the calculation goes 1 minus 1 over k squared. So that'd be 1 minus 1 over 2 squared, which is 1 minus 1 over 4, which is 3/4. The example in the slide, in the last slide, also had the same numbers here as well. So that comes out again to be 75%. So the answer to the question, at least what percent of scores lie between 62 and 154, at least this much would be there. So in the next part, what we need to do is solve so that we can figure out what percent for at least 84% of scores lie between two values. In this case, we're going to basically need to solve for the number of standard deviations. So what we're going to do is we're going to take the formula here, 1 minus 1 over k squared, and we're going to set it equal to the percentage value and then solve for the number k. So that means in this case we'll solve 1 over k squared is equal to, well, we need to actually convert that to a decimal as well before we use this here. So it had 84%, so as a decimal, 84% would be 0.84. So you can solve this. I'll go ahead and go through the steps here of solving. You might be fairly familiar filling with these things, but I'll just go ahead and do it just in case. Subtract 1 from both sides, and that'd be equal to negative 0.16. And then let's multiply both sides by negative k squared. That way it'll change to positive 1 equals positive 0.16 k squared. I'll divide both sides by the decimal, so k squared is equal to 1 over 0.16. And then take the square root. And we're just going to do positive square root in this case. And so k is equal to the square root of 1 over 0.16, which comes out to be approximately rounded to 2.5. So the way that we interpret this number k is the number of standard deviations from the mean. So what I'm going to do next is I'm going to take this number 2.5 and I'm going to times it by the standard deviation. Standard deviation being 23. That comes out to be 57.5, which I'm just going to round that up to 58. Okay. And that is the distance from the mean that we're going to travel on either side. So if we start with the mean in the middle, 108, and we add and subtract this number to it, that'll spread it out to 50 at the low end and 166 at the high end. So our answer is at least 84% falls between 50 and 166.